Problem number 3. A mercury barometer reads 26.45 inches. What would be the corresponding reading of a water barometer? Letter B. What is the approximate elevation above sea level, assuming normal atmospheric conditions? So first is, let us answer what is being asked in letter A. What would be the corresponding reading of a water barometer? So we have here a mercury barometer that reads 26.45 inches. So this is your height. So first is we have to get the pressure as per mercury barometer reading, and then what is the equivalent reading in water barometer. So pressure is equal to the unit weight times the height. So in the problem, the unit weight of the mercury is not given, but you know that the specific gravity of mercury is equal to 13.6. So this is a constant value. So in a given problem that the specific gravity of mercury is not given, it is always 13.6. So knowing the specific gravity of a fluid, we can get its unit weight. So this is simply the specific gravity of the mercury, which is 13.6, multiplied by the unit weight of water, that is 62.4 pounds per cubic feet, multiplied by the height, which is 26.4 inches. So we have to convert inches into feet so that the unit is consistent. So we know that 12 inches is 1 foot. So your inch and your inch will cancel out, and then foot and the feet also will cancel out. So this is now 1,867.008 pounds per feet squared. So note that this pressure is absolute pressure, because based on our previous slides or previous discussion, mercury barometers or barometric pressures are always absolute pressures. So since we already know the pressure as per mercury barometer reading, we can now get the water barometer reading. So that is the pressure 1867.008 pounds per square feet is equal to the specific gravity of water, which is 1, multiplied by the unit weight of water, which is 62.4 pounds per cubic feet, multiplied by the unknown, which is the height of water. So from here, the height of water is 29.92 feet. This is now our answer for item A. Next is for item B. What is the approximate elevation above sea level, assuming normal atmospheric conditions? So note that we already have a value of absolute pressure, which is 1,867.008 pounds per feet squared. And then under normal condition, since it says in the problem that under normal condition, we have a constant values for atmospheric pressure under normal condition. So for atmospheric pressure, that is equivalent to 2166 pounds per feet squared under normal condition. So note that absolute pressure is equal to the atmospheric pressure plus the gauge pressure. So we already have the value for the absolute pressure. We have the value for the atmospheric pressure. We can now solve for the value of the gauge pressure. So our gauge pressure now is the absolute pressure, which is 1867.008 minus atmospheric pressure, which is 2166. So both are in pounds per feet square. So this is 298.992. So the negative is an indication that this is below the atmospheric pressure, or this is your vacuum pressure. So we know also that gauge pressure is equal to the unit weight of the fluid multiplied by the height. So in our case, since we are not referring to fluid, we cannot use the unit weight of fluid, but what is being asked is the approximate elevation above sea level, meaning to say this is atmospheric height. Since there are no fluid involved, we can use the air density. So the air density is given to be 0. This is what we will be using since this is in English units, 0.0765 pounds per cubic feet. So we substitute. So this is now the atmospheric height is equal to the gauge pressure, which is 298.992 pounds per feet squared, divided by density of air, which is 0.0765 pounds per cubic feet. So pounds and pounds will cancel out. Feet, 3,908.392 feet. Answer.